Hi, everyone. So today we have Maxime Bergeron from Riskfuel, who'll be talking to us about Hilbert, deep neural nets, and empirical moduli spaces.
All right. Well, thanks for the invitation. So I guess that this is going to be an interesting talk, kind of a hybrid of math and empirical stuff. I know you guys had Luis earlier, so I made sure that there's kind of no overlap and it's really complementary talk. Not assuming any background, but I go about it quite differently than he does. So hopefully people will feel inspired in some way. So the title is meant to kind of poke your interest. Hilbert, what does Hilbert have to do with deep neural nets, and what on earth does that have to do with moduli spaces, and what is an empirical moduli space? So hopefully all of that gets answered in due time during the course of the talk. Oop. All right, I need to hide the chat. All right, so the kind of motivational story here is that as humanity, we're always trying to solve harder problems with the latest technology. So here I have something we're all quite familiar with, mainly the quadratic equation. And I've kind of written it in a little bit of a funny way because I want to think about it as a family of problems. And for each of the parameters of this family, we output the solution. So here I'm putting the equation on the left, and on the right-hand side, we have the solution. So, it could be empty if you're working over the reals, could have some multiplicities and all that jazz. And I'm really thinking about this as some operator, which is going from some family of gadgets to some space of solutions corresponding to those guys. And in this case, it's not so clear. I mean, really, we can think about the equation itself as spitting out the solutions. But if you kind of specialize to more restricted equations, it becomes more obvious what we talk about. So if I write z squared plus 2 equals 0, then everybody knows, there's two square roots here. And so really, the equation is implicitly defining a multi-valued function. And in this case, the operator we all know as square root. Now, I say I'm kind of leading up to this, but so the Babylonians were the first to kind of, I guess, put two and two together and say, hey, we don't need to think about the full quadratic equation as just a single widget. We can kind of break it up into steps. And what we think about as the quadratic formula, I really want you to shift your attention and think about it as a composition of simple binary operations. So in order to go from the full family of equations on the left into the solutions, we really start step by computing the discriminant, then computing the square root of the discriminant, combining that with plus with minus b, and then applying the unary division onto it. So it's really about breaking up complicated things into sequences of faster things. And kind of this is where the pure / applied kind of join hands. From a pure point of view, we're trying to just write solutions as operators, as a composition of easier functions. And the kind of applied side here is that you get to switch off time and accuracy. So presumably, you could have pre-computed tables of square roots, and then you know how to add, multiply, and divide quite quickly. And so then you could use those to spit out the solutions of a quadratic on the fly. And kind of this, I want to think about as a template for everything all the way up to deep learning. So let's fast forward to the 1800s. And there's kind of this lost art, which was making this kind of idea practical, which were called nomograms and nomography. And the idea was, once again, you want to pre-compute the hard binary operations. And then the trick was you want to represent them graphically for fast inference. We don't have calculators. We're out in the field. We need to solve quadratics. Here's a nomogram. Like you recognize clearly there's a quadratic-like shape going on here, but it's not exactly what you think. Here, the x-axis is the input p, the y-axis the input q. I don't know if you can really see here, but it's looking at the family x squared plus px plus q equals 0. And if you want to find solutions, well, you just find your p, find your q, draw a line through them. And at the intersection here, you're going to have a gradation. And you see here that you get the answer 2 in this case. So these are kind of handy little, kind of like slide rules, but a little bit better because you get to be all nonlinear about it. And
you have two intersections here. So the other one is the other solution.
Exactly, the two solutions. I guess I messed up. I need another dot there. But yeah, it gives you the two solutions. And of course, if you try to be fancy and pick this point here and that point there, you see that it doesn't intersect. And clearly that's telling you that that has no real solutions. But these are kind of cool gadgets that were forgotten. And in the process of preparing for this talk, I was kind of wondering, how do you build these things? And there's some kind of neat little linear algebra, which is basically if you're trying to represent some equation in terms of collinearities in the plane, you have this idea that 3 points are collinear if and only if a very specific determinant vanishes. And so the idea is any kind of binary operation that you can somehow massage as being represented as some determinant. Then once you have it as a determinant, you can do some kind of matrix operations to make sure that there's all ones in the last column. And that is kind of what gives you the way to move the lines around in nonlinear fashions to get these kind of diagrams. So there's a whole world here that was abandoned, with computers. But I think it ties into algebraic geometry a lot, right? Because you're trying to encode some nifty relations between things in a graphical way. So that was kind of the state of the art in the 1800s. And you can kind of play this game in a chain fashion, right? So you can have several nomograms on a same page and use them to build up solutions to harder and harder equations. And so in this case, speed and accuracy is paramount when your life depends on it. So if you look over here, this is something about estimating the speed and intensity of a forest fire when you're out in the field. And so you got all these kind of percent slope, wind direction, effective value of wind speed, I don't know, moisture of the live foliage, moisture of the dead foliage. And you're kind of running around this diagram trying to figure out exactly how quickly you should be watering that area or running away for your life. So that's just kind of, there was a whole world of these things out there before. And we do think about finance problems, and this one I understand a little bit better, so I can actually walk you through it. But here's an example of a kind of nasty, well, not that nasty, mildly nasty looking partial differential equation. And you might be wanting to find some solutions of this. And on the right-hand side here, I've got this nomogram that allows you to really quickly and without knowing anything about PDEs or even math, find some solutions. So it has lots of terms, this V, this T, sigma, I mean, whatever. They're called maturity, interest rate, volatility, normalized spot. And the idea is that you can decompose a solution to this equation as a sequence of steps. So here I kind of circled some value, 10 for the 10% interest rate, 8 for the maturity, 60 for the vol, and 130 for the normalized spot. And the game you play is you start at maturity, and then you draw lines to the corresponding nonlinear encoding of the other two variables. And then you kind of chase around the diagram. So you go all the way to this line, and then you find the coordinating matching point here. And then voila, you found the answer is 34. Basically, you don't need to know anything about anything, and you can do this very quickly on the fly. And the bonus of these approaches that you can get, I guess in finance they're called sensitivities, but you can get partial derivatives very easily. So I can say, hey, what if I wiggle a little bit? How does the value change? And it's just as simple as doing this. And you can see, hey, if I wiggle the whatever this variable down here is, I get kind of this much effect. So 34 becomes a 31. So it's a pretty big one. And if I wiggle this volatility parameter, I see it doesn't change all that much, 31, 29. And you can just eyeball these things. So I think these diagrams are kind of really cool, and they're really getting to the heart of the matter that you want to build up. You want to kind of abstract away the hard pieces so that when you need it, you can just get it really quickly. Are there any questions about this stuff before I dive in? This is just kind of an appetizer. All right, so what does this have to do with Hilbert's 13th problem? So his motivation actually, I mean, okay, as a pure mathematician, we all know this is not really what he was after, but if you go back and read his original statement of the problem, he does kind of point it out as a problem of wanting to split up time and accuracy of problem solving. And for him, it was very specifically, he wanted to conduct ambitious engineering projects. Namely, his favorite example was the French railroad. Right, so when you're trying to build a railroad, you need to even out the ground. So you have to do these cut and fill computations where you want to, dig up the earth here and move it there to make everything nice and flat. And that's very difficult to do on the fly. So if you have these kind of nomograms to help you out, in fact, they did, and that is kind of the only way they were able to efficiently build the railroad. So I actually think about, it's Hilbert's 13th NSERC application because he was very concerned with making his work applicable and interesting to people outside of pure math. And I think he did a fantastic job of that. So what was his approach? Well, he said, hey, we have these nomograms, and he found a nice class of functions that he knew you could always solve these problems about the little determinant and massaging it into the right shape. And the class of functions he was thinking about was compositions of algebraic maps of at most 2 parameters. So what do I mean by that? Well, here's an algebraic map of 1 parameter. Namely, I have a polynomial equation with 1 free parameter, namely the q. And the map from this to the solutions, that is an algebraic map of 1 parameter. The one we're all familiar with is mainly radicals. So any radical is an algebraic map of 1 parameter. In that case, you just don't have these extra z terms in between. And geometrically, I really think about this as we have this blue line, which is the q parameter moving around. And above the blue line, we have the solutions. And you get some multiplicities. Sometimes you might have no solutions. I guess for a cubic one, you'll probably always have one. And yeah, so this is kind of how I think about an algebraic map of 1 parameter. And then, you could also have 2 parameters. So here's a quadratic. I've got a p and a q that allow it to move around. And, in this case, it gets a little more fancy. You're really looking at a branch cover. But basically the idea is the same. Think about a plane lying underneath this, and above each point in the plane, you have all the corresponding solutions. And basically, if you're looking at any of those kinds of maps, you only have 2 parameters and 1 output, then you can build a nomogram because you have one funny curve for the first one, another funny curve for the second, one curve for the solutions, and you can just have at it like we were doing earlier. And the challenge that you kind of left to people was, can all families of polynomials be solved using such maps? So this is kind of a generalization of the fact that we all know that we can solve polynomials up to, I guess, not up to degree 5, but degree less than 5 in terms of radicals. And in fact, you can do the polynomials of degree 5 using these things called Brigg radicals, which are actually maps of this form here. It's actually, I guess, z to the 5 plus z plus a equals 0 in that case. And for this degree 6, he was able to do it using 2 parameters. And then he had a very specific equation of degree 7 that he tried very hard to reduce to such a form, and he couldn't do it. And he kind of left that as a puzzle to see if people could solve it. And that was his 13th problem. Are there any questions about that? Okay.
Doesn't look like it.
So here's the funny thing. So, Kolmogorov and Arnold came along and said, hey, Hilbert, there's no such thing as a truly multivariate continuous function. So that kind of seems like a counterintuitive statement. And it is kind of stated tongue-in-cheek. So I've asked some Russians to read their actual original papers, and they do say it's kind of said as a joke when they said, yeah, we solved Hilbert's 13th, but they kind of purposefully slightly misinterpreted it to talk about continuous functions. And they said, well, hey, if you have continuous functions, here are some, f of xy is x times y. That sure as hell looks like a multivariate function. There's another one, also looks like a multivariate function. But what Kolmogorov and Arnold tell us is that these are actually secretly nested compositions of single valued composition and addition. And addition is kind of the only multi-valued function out there. So how do you do it? Here, you use things like exponentials and logs. You can decompose multiplication as a tower of one variable function, log x, don't need anything else, log y, don't need anything else, combine them with plus, and then you got x of a single big blob, and so on. You can kind of have at it for any individual function and split it up as a tower of this shape. And the theorem they prove, which is kind of insane, is to say, you could do this for all functions at once. And the way they do it is, the exact terms of this expression aren't all that important, but basically there's this little phi and this big phi. This little phi is universal. It's the same for all functions of a given dimension. So you give me any function with n inputs, there exists a universal little phi. Lambda p is a set of constants. Once again, it depends on the dimension. And then q, that's nothing. That's just a summation index. And eta is one fixed number. And basically, this inner piece here does not depend at all on the actual function f. And then they have one extra nonlinear function phi, summing it all up, and they can actually get equality on the nose for any continuous function. So this is kind of a crazy theorem. And this is really a statement about how insane continuous functions are, right? The fact that there exists this one continuous function here that can kind of do this all at once is telling you that there's something kind of not entirely kosher going on under the rug. But I think that there's actually a lot of value in this theorem, even if it's just an existence theorem that you wouldn't be using in practice. So I think about it as any continuous function, there's this universal change of coordinates that turns it into a sum of things with some nonlinear factor added to it. And I think about this as, you take a touch of nonlinearity, and that's just this phi and this phi, and then a good dose of linear algebra, and that's all continuous functions. That's how I think about Kolmogorov and Arnold. And then the question is, well, can we actually make this effective? So we know this representation exists. What can we do about decomposing functions in this way? And so, in theory, there's no difference between theory and practice, but in practice there is. So theoretically, we know we can do it, and how do we have at it? Any questions about my hand-wavy treatment of this theorem?
I'm just laughing.
Yeah, it's a funny theorem. Okay, so we have Hilbert's 13th problem, Riskfuel's first problem. So how did I get swallowed into this beast? And it's actually, so I should tell you, so before I started working for Riskfuel, I was definitely thinking about Hilbert's 13th problem, and it turns out that there's quite a link there. So what are these guys doing? They're doing the same thing. They're saying, hey, we have a family of stochastic partial differentiation, family of stochastic partial differential equations. You may have some methods slow and noisy to compute individual solutions. So you should think about, you have your quadratic formula and you have these kind of clay tables where you've pre-computed those radicals. How can we kind of generalize to this context? And it's even more vague than that. We have a family of problems. They don't have to be weird PDEs. You just need a family of problems and some kind of a method to try and get some answers in some cases. And then the problem is, can we use this idea that there exist these representations of anything continuous as a touch of nonlinearity and a good dose of linear algebra and find that kind of representation? Spoiler alert, yes, you can. And I guess we're going to talk about how that works. So it turns out the answer comes from these things called deep neural nets. So how do I think about deep neural nets? I think about them as a touch of nonlinearity and a good dose of linear algebra. So what do I mean by a touch of nonlinearity is I choose a single non-polynomial function. Let me call it sigma. You've got here a classic example, the ReLU. This is a non-polynomial function. It's just straight line, as easy as it comes. And you start composing that over and over again with some affine transformations. So, what's an affine transformation? It's just a linear transformation plus you get to translate it at the end or before. And so a deep neural net is really just that. You got a sequence of vector spaces and you alternate between applying your affine transformation, applying the non-polynomial function, applying the affine transformation, non-polynomial, and so on. And the idea is that somehow by using this specific class of functions, you can actually make those other theorems kind of effective. So here's my kind of meta representation of a neural net. I've got my vector spaces, and these black arrows are basically joined together, the affine transformation and that nonlinearity applied right after it. So that's deep neural nets in one slide. Why such the hype? So here's a meme. And the guy just discovers, hey, deep learning is just all matrix multiplication. And once you can't let you go on with your life. But basically, no matter how fancy people are doing, so here you're seeing long, short-term memory cell, crazy nonsense. It's all just special block forms of affine transformations and nonlinearities. There's nothing more to it ever. But why do we like this class of functions? What's so special about this? Well, so say we want to represent some function. So we have our crazy multivariable function going from Rn to R. We actually have a method to try and find a kind of representation in terms of it. So the idea is basically gradient descent. So if you know some values of this function, you can just build some crazy composition of this type, evaluate it against a known point value, see the difference, and then move along the gradient of the difference to try and hope to find a better and better representative of those functions. And the thing that has really made this come to life is that the simple structure here, it's basically all matrix multiplication, means that you can do this really, really well with GPUs. So maybe why are GPUs good here? Basically, GPUs in gaming, when you're trying to simulate some kind of effects, you typically need to be shading images. And shading images turns out that you want to do lots and lots of operations in parallel to capture them. And that lots and lots of operations in parallel is basically baked into GPUs, and so you can use them for this as well. So that's kind of the thing there. And this was a bit confusing to me actually when I first was thinking about it. So I thought I'd have my secret deep neural nets for mathematicians. I guess this is an applied algebra seminar, so I snuck in a tensor product. But basically, let's think about a single layer deep neural net. So we start Rn, that's the dimension of our function. We apply some affine transformation, we do our linearity, and then we apply a second one to get out to R. And that's basically our function. So what am I saying when we're taking the gradient? Basically, let's forget about the nonlinearity just for simplicity. So we have two affine transformations. And if X is the input here, we apply the transformation, we get X1. We apply the transformation, we get Y. And what we're really doing is we're taking the gradient in the dual space. So we're kind of using this one-to-one map between homomorphisms from Rn to Rm, identifying that with the tensor product of the dual, and basically shifting coordinates. So we view the map in its own coordinates as the input, and here alpha 0 and alpha 1 are evaluation at x0 and evaluation at x1. And this is where the gradient is really happening. Somehow they don't say it like this in deep learning, but that's what's going on. Then of course, using this, you can come up with some pretty neat, I guess it's kind of a linear algebra / calculus exercise to figure out how to compute those gradients effectively. And you'll get some nice formulas, but as pretty as they are, they're not quite useful for actually computing things. And the computer scientists have figured out a better way, in quotes, to do linear algebra backwards. But just a warning in case you decide to go and actually look at implementations in code. Any questions about that?
Well, will you spend some time with that better way?
Well, the better way is that we should not use Euler notation for functions. So computer scientists do not compose functions like we do. And so they actually, they transpose everything so that if you're trying to apply matrix 1 after matrix 2, it really is, read from left to right. And then that way you can actually do it in batches. But it's just a warning. So somehow when you look at their code, it's extremely confusing at first because you think they're writing it wrong, but they're just doing everything mirror image. I guess it's like the French and English notation for tableaus. You gotta, I guess, use a mirror and look at it backwards or something like that.
Well, the Russian always compose the other way.
I guess they know what's up in terms of putting people on the moon. Not the moon, but the space first. Maybe that's why.
Yes. Okay.
All right. So, I've just given you some class of functions. I've told you we can play these games with it. Does it actually work? All right, I haven't given you any indication of that. And so deep neural nets in theory, here I put, exclamation, interrogation, because it's a one-layer deep neural net. It's got input, output, and a very big middle one. And the interesting theorem is that using a single hidden layer, you can approximate anything you want uniformly on compact sets. And so somehow there's no restriction there at all. Of course, you say, what's the catch? Well, the catch is this middle layer has to be exponentially large, which is actually just completely impractical. So we're kind of chasing our head in circles. But we do have some kind of quantitative bounds, which is that you can control the error actually in terms of the number of neurons. So here, I guess that's the first time I use the word neurons, but neurons is this dimension of the hidden layer here, like M1, and the number of known function values, right? So the number of times that you actually were able to evaluate this function that you're aiming for. So somehow there's a push-pull between all those variables. But this gives you some hope, using a single layer, you can actually get it done. Here's a kind of long string of people proving stuff about that. They did it for sigmoidal, not sigmoidal, et cetera, et cetera. And I guess the cool thing is, you take your favorite, any function. So this nonlinearity here, it doesn't have to be a sigmoid. It doesn't have to be anything specific. As long as it does not satisfy some polynomial relation, you can get any function you want. So that's kind of a very, basically this says that you can be fairly creative with your choice of the sigma. And I would say that the Kolmogorov-Arnold theorem is taking that creativity to the extreme and coming up with a single and insane function that will do it all. So I'll leave those there. So that was with a single hidden layer. And then, well, you have still deep neural nets in theory, now actually deep. And you have another approximation theorem that says you can actually fix the width to be actually, I think, 1 or 2 more than the dimension of inputs. And then you allow yourself to go arbitrarily deep. And then you can, once again, you get the same result where you can approximate arbitrary functions uniformly on compact sets. So somehow you have this dichotomy. You can, be very, very shallow and very, very wide, or very, very deep and not very, very wide. And the art is kind of figuring out what you should do between these two variables. So, we can, as a user, you're free to play with the width and the depth. And the kind of quantitative results tend to be along the lines of shallow networks need exponentially more neurons than deep ones. So here's a shallow network with 2 layers that has to be huge versus a nice, even just 3 layers can be that much better. Does anybody want to venture a guess as to why 2 and 3 is a nice example here? What kind of function do you think would be way harder to do with just 2 layers than 3?
No guess.
Quadratic versus linear, or
Quadratic what?
quadratic versus linear, or
I guess more fancy than that. if you have any kind of, oh, the word's escaping me. 3D coordinates. What's the word? If you have a function that has a three-dimensional rotational symmetry, you can do it quite easily using just 3 coordinates. And then that translates to 3 small layers, but you can make it kind of wild enough that with just 2 layers, you're kind of out of luck. And so people have some nice explicit examples of that. But basically, here's another hint, I guess, symmetry comes into play. So all of these theorems are actually for arbitrary functions. So f, I haven't said anything about it, but of course, in practice, you get to peek at f and you know what you're dealing with. So if there's some symmetry, you might want to bake it in. And the way you cook up those kinds of examples where you show these really dramatic drop-offs where it's impossible to do with just 2 layers is by kind of exploiting symmetry in that way. So here's just a bunch of resources for people who are curious about shallow versus deep and what gives. So deep neural nets in practice. All right, so I feel like a lot of people actually give a lot of hate to those existent theorems, and they say those are useless because look at me, I just went on TensorFlow and I built a neural network with a single hidden layer, and I went up to 20,000 neurons and I couldn't do any good on this particular data set. And the answer is, well, you shouldn't be using that, right? You should really be using your domain knowledge, and you should really be tailoring your approach to the specific things you're dealing with. So there's 3 kind of things I want to highlight that matter a lot more than you think. The architecture matters. So we already saw like wide versus deep and so on. And then special matrix forms, that's basically all these other funny words you hear about neural nets is basically people finding clever ways to build some sparse matrices in some ways, have some linear transformation affect ones that are farther down the line while skipping the ones in the middle and so on. The training data matters. So, you have your function, you're able to evaluate it in some places. You don't just necessarily want to pick some points at random. You really want to make sure that you're controlling both the quality of your data. So sometimes you can have, if you have a Monte Carlo simulation, for instance, you can dial up or down the accuracy, and we'll see how that comes into play. How much do you need and where do you place it? Those are kind of 3 rather important variables. And then the training method matters. So this stochastic gradient descent I was talking about, it's just the beginning. Here are some interesting lost landscapes. And if you're in this kind of weird egg world, how are you going to make sure you don't end up in one of these little shallow plateaus and make it to an actual good representation and so on. So there's a lot of like actual empirical stuff that goes into it beyond just these existence theorems. And sorry, I didn't know what order my slides were going in, but so here's data requirements. So for this net, I'm using these ReLUs. So that was this flat and then kink activation function. And basically what that means is that we're living in the piecewise linear category. And so you can see that here's so the blue curve in the background, that is the function I'm trying to approximate, basically a sine function. And then I've just dropped some training points, meaning places I've evaluated the function on it. So on this left-hand side, I had a few points. I added more here, and here I added quite a bit more. And then the red line, or I mean the red curve, I should say, is what the deep neural net is doing with that data. And you see here, it's not doing so hot. It's doing a straight line. And in fact, if you zoom in close enough, you'd see a bunch of broken straight line approximations. And that's basically what ReLUs do. And so basically here, we just got a little unlucky. We're just throwing points at random. And we see that there's just a point out here. And then there's a whole portion of the curve that doesn't have any points on it. And so of course, you're getting a bad approximation there. And this one, you're already filling up a little bit there. And you see it's already doing pretty good. And when you add lots and lots of points, you get essentially perfect fit everywhere. So this is just telling you kind of how this training happens over time. Now, there's this other really interesting phenomenon, which is that deep neural nets love low frequencies. So I'm playing the same game here with there's this thing called the frequency principle, where deep neural nets, empirically, when you're training them, you notice that they fit low frequencies first and higher frequencies later. So they're not just learning the function as is. And so what you see is that basically, once again, I have my ground truth, which is the blue curve. And then you see these little blue dots that are clearly not on the blue curve. And the reason that is that we evaluate the function and then we inject some noise. So we pretend that we had this very, very bad method. And so this is as good as we can get in terms of generating points on the function. And you see, we don't have that many of them. The red line is not doing so hot. As you add more, the red line starts doing better. And here, this is extremely noisy data. And somehow the neural net is able to figure out that this is actually the curve it should be learning. So somehow noisy signals are not a problem, and deep neural nets are extremely good at learning from completely messy data. That's another kind of interesting feature. And the last one is a quantity beats quality. So you might think, hey, I want to evaluate my function extremely, extremely precisely at a bunch of points, and that's going to give me a better fit. And what we're seeing here is these two first ones. So there's the same compute cost. So here we have a bunch of points, and they're extremely precise. So they're right on the blue curve. Similarly here, we have a bunch of points, extremely precise, right on the blue curve. And the fit is not that great. It's still kind of bouncing around with weird kinks. And here we have a ton of points of extremely low resolution, so you can get them essentially for free. And we see that we actually get a better fit with that. So somehow the quantity of data beats the quality of the data that you have. And here's one to illustrate, you got to be smart about data placement. So here I've got a blue function I'm trying to learn, and it has this weird jump here. And we see that here I'm just putting some points uniformly at random, and we see that there aren't any super, super close to the edge there. And so the fit is not quite good. But if with the same number of points, you space them out nicely and you make sure that there are some at those places where the function jumps, you get a nailed perfect fit. So this is the mantra here is, use domain knowledge to your advantage. You want to peek at the function and you want to really make sure that you know what you're dealing with, not just fly blind. And this is the mandatory, just a promo. It's the only slide about it. But basically, Riskfuel in finance, there's a lot of really high dimensional messy things like that, where you only have a super slow Monte Carlo thing to try to get values. And we did this, it's called the Bermudan swaption, right? Write a name. So basically there's two kinds of options. There's American and Europeans, and there's some that are kind of a little bit of features of the first and a little bit of features of the second. So they call them Bermudan, somewhere in the middle. So Bermudan options are notoriously kind of difficult to price. And we kind of built this demo. And here you have on the left-hand side, this is basically a deep neural net, which is finding value like 252.2 in 0.02 seconds. And it's computing all the partial derivatives at the same time, versus a slow Monte Carlo, which is going to give you the exact answer, 251.9, but that takes 7.7 seconds, and you don't know any of the partial derivatives. So you can see that if you're running this kind of computation, all day long, you're going to be sitting there a while, and you might want to opt for something like that. So if you're curious, you want to just go play with it, there's actually a nice little app that we got on there to see a neural net in action. All right, so it's a algebra seminar, so I've reserved the right to speculate, and maybe this is the part where you can tell me what you think. But basically, we have problems where we can kind of fit them in this framework. So, given a family of algebraic problems, the one I'm thinking about, you have the word problem in groups, solvability of Galois groups. And you have a method, slow and noisy even, to compute individual solutions. So the word problem, we have some algorithms, they may or may not terminate, but you could still try and get some data points or even some confidence. You could say, hey, if I run this algorithm for this many amount of time, I'm going to call that this much confidence. Can we kind of build neural nets that would give us kind of quick and valuable feedback on conjectures, right? So you're trying to figure out if something is solvable in some way, and then you compute a bunch of examples, and then you train a neural net on that, and it's going to kind of allow you to do some inference to try and see between the lines. So, the interesting thing is this will give you some feedback that is not human, right? So it's going to be kind of very orthogonal to perhaps the way that you think about it. And I think that even if the feedback is wrong, there might be something interesting to do there where you can kind of play a game with some neural nets and try and go back and forth with them. The example I think about is actually the game of Go, right? So basically AI was able to beat humans, but then the humans, by looking at the way the AI was playing, were able to become even better players. So somehow it's a whole new way to look at things. And then a second speculation, you might have some. Let me think of Hilbert's problem, right? So Hilbert has this degree 7 polynomial, and he's saying, I don't think there is a way to write it as a tower of algebraic maps of at most 2 parameters. And so you could hand build a net where, I know I said that the activation or the nonlinearity has to be a non-polynomial, but I don't need a theorem, I just want to use it. So I could try to build some neural nets where I bake in some polynomial nonlinearities instead of non-polynomial ones, so that I stay within the category I care about, and then try to see if I can start from certain architectures and do some kind of gradient descent thing and try to see if the representations I believe exist actually exist. So this is speculation number 2. Right? You have some map, you suspect that you can represent it in a simpler way, or you have some presentation, you suspect it would be a simpler one. can you kind of build a net to try and then try and reward it based on simplifying that presentation and see if you actually get somewhere. So those are speculations. I don't know if anybody has anything to say about that.
Yes, I have a lot. This is where Luis generated a bunch of conversation in his talk, and so let's try.
I should say I have 2 speculation slides. So this is speculation part 1, and then we're gonna do a little bit more, and then there'll be speculation part 2. So
okay, so let's say you have a problem where you can conjecture, where you can compute examples for small amounts of, for small data, and you want to try and say, you want to come up with a solution for larger data. Is this sort of problem, are neural nets or sort of thing where you can apply it to it, where you can say, well, yes, it expands, it can interpolate that data which is further out, because you're not going to be able to sample those further out.
Yeah. So I mean, I have no theoretical theorem to tell you that it will work. But here's the cool thing, you just do it, and then you'll see what it tells you, and then you can humanly interpret it. And I will say that I have personally gone way out of sample on a bunch of nets, trained in a bunch of weird ways. And as much as people say, oh, all bets are off the moment you leave the training domain, that's not necessarily true in practice. And I think that you want to play this game, right? So, it's kind of, you're going to want to start small. So say you have examples going out to, I don't know, 100 dimensions or whatever. 100 is arbitrary. You might want to play this game where you train it on the 100 dimensions, and then you train it just on 50 dimensions, and then you try and see how well it would have done on this extra domain that you had. And then that can help you figure out exactly what kind of neural net you want to build, right? So you might notice, hey, if I go shallow and very wide, I get really terrible generalization, even going from 50 to 100. And if I go deep and very skinny, then all of a sudden my generalization is better. And then you can use that kind of as a guide. And then of course you train on your whole data set, and then you go and kind of see what's out there and try to interpret that. So I think that the ability of neural nets to generalize out of sample, people don't like to use it because there's no theoretical foundation, but empirically, if you're not doing some insane GAN thing, it's not as bad as you think.
And then what's involved in training? So you use that word and didn't quite.
Sure. Oh, so training is just gradient descent. So you have your net. It's going to spit out some answers that are going to be garbage, and then you basically evaluate the gradient against your known examples to try and nudge it towards a better. So it's kind of like, maybe I should go back to the slide. So here's a very simple neural net. You have a W1, which is some affine transformation. I just think about linear transformations. You have a matrix W1, a matrix W2. The sigma is just fixed, so you don't care about that. And training is just changing the entries of the matrices representing W1 and W2. And the way you do that is you evaluate an example and then compute the gradient in the dual space and kind of follow down. So you kind of, that's what training is. Training is just gradient descent. And it was confusing to me initially because there's 2 functions going on, right? So there's the function that you're building, which is the neural net, and then you're kind of taking the gradient with respect to the coordinates of the pieces of the neural net.
Okay.
I don't know if that is more confusing or less confusing.
I'm done asking questions about speculations.
I would say that it's not more confusing or less confusing. It's just that unless we actually do it personally in practice, it's really hard to
honestly, the way I figured it out is I made this 3, 9, 1, and then I just wrote out some matrices and did it. And then I got it.
Exactly, that's what you have to do.
You have to do it. Otherwise, it just sounds like, but you can just think about it as, you have affine maps, and everything is in a coordinate. So I have a fixed basis. So, you can change the coordinates of that map. Imagine it's a 2x2 matrix. It has 4 entries, and you can wiggle those matrices around. And basically what you're doing is you're seeing the prediction your net is making, comparing it to what it should have made, and comparing the gradient with respect to the coordinates of those matrices, and then taking a little step in that direction. And that's what this is saying. So this here is a graph of the coordinates of the matrices that represent the affine maps. And so you're kind of moving around.
And how hard it is, you know, like we are dreaming about that somehow. We are saying, you know, like, can we start using that to do pure math or solving our stuff? How hard it is to actually use.
I
so
mean,
we learn, you know, like to do symbolic manipulation, and we are all in Sage and things like that. And then the next step might be to be able to use those network. And
I mean, I'm sure that you could probably tie in symbolic manipulation in Sage with a nice deep learning library, and then get the ball rolling.
That will be our next step. Yeah.
I think the hard part for us is learning how to encode, like what's a nice, you know, given a data set, how do you encode it? And then how do we know that that's a good representation?
Let me show you. I think my next few slides are going to maybe give you some ideas. Let's pause this speculation. And then I'm going to talk about a little bit this other stuff. So there's the empirical moduli space. So if you don't know how to encode your data, the mantra is, well, don't encode it. So here's a weird looking neural net. It's the same thing as before, but I had the bigger layers and they're kind of shrinking down to a small layer and then going back up. And my output is actually my input. So it's called unsupervised learning. I'm just putting in the encoding. So you have your combinatorial structure, whatever, you know, it's a vector at the end of the day. If you're doing symbolic manipulation, you have to be able to encode things as just a discrete thing. You feed that through this beast and it comes back out on the other side. And here you're penalizing it, not based on something that you want. You're just saying, hey, I want you to be able to reconstruct exactly what I fed you in. And it's trying to construct a lower dimensional or sparser representative of that data in a way that it can go back and forth. So you can think about it as compression, decompression. And I mean, here's just an example. So, I mean, for me, I'm thinking about these weird things called volatility surfaces, which are just surfaces with some kind of geometry. And then you feed it in through this beast and you want to make sure that the thing that comes back out on the other side looks close enough to the thing you fed it in. And then the idea is you train this thing, and then after it's trained, you go in and you peek in the middle to see how was it encoding what I was feeding it in. And then that gives you hints about the behavior of the object you're trying to understand. And there's another complexity. Basically, this is like manifold learning, or you could call it even combinatorial manifold learning, where you're doing two things really. You're penalizing whatever this gadget is for not reproducing the thing you fed in, and you're trying to make it put some kind of structure on this middle compression layer. Let's get that. And basically, what you're doing is you're getting three things in one. So you have this encoder half, which is the compressing theme. You have the latent space, which is the compressions themselves, and then the decoder half, which is the thing that goes from the tight thing back up to the original structure you had. So if you're in Sage, you would have your crazy combinatorial thing here. You feed it through this, and then you want to see what's going on in here in such a way that it's always reconstructible.
In this sense, are you always choosing your latent encoding to be just like a very small, short layer?
So stereotypically, yes, but you could also make it a big layer, like a 100-dimensional layer where you only allowed 10 things to be non-zero at once. So you can play that game too.
Well, so it's a little bit, Mike, if we were to say the coefficient of the irreducibles.
Yeah, exactly. You have your coefficients, and then you're trying to see if there's a way to find an expression with less coefficients. So I mean, that's a great example. Just take a thing.
Or dimension or something like that.
Yeah.
If it's one number, you put dimension. So from the dimension is kind of weird, but the encoder, this assume that the encoder and the decoder can decode, which is kind of that depends on the symmetry of the things.
You don't assume that it can decode. The network is just trying to decode it, and all these things. So basically, these little lines here is just basically those affine transformations. People usually draw them like this.
Well, we know what those lines are.
And everything is being trained at once. So like the encoder and the decoder are not the same necessarily.
No, I'm not
saying that if you want.
I'm not saying that they are the same. I'm saying that the fact that there is a decoder seems to imply that from the latent space you can
Exactly.
recover.
Exactly.
So
the fact that
you have to have to very specific.
Yeah. So
in
you
order
have
to do that.
If the decoder is able to reconstruct your thing, it means that I would call it the intrinsic dimensionality of the thing you're trying to compress is lower. So like, let's just keep running with surfaces. I think it's a good example where, I mean, here's just to give you, so after you've trained it, so you've run examples through it over and over again, and you've moved all these little arrows in such a way that it's doing pretty good at reconstructing and pretty good at giving a structure, then you can do three things with it. You can use it to encode, so you just chop off that half and then you feed things in and you get these smaller dimensional representations. So that's the encoder half. Conversely, you can chop off the encoder half and then you can just move around in latent space and see what's out there. So you have any two numbers, in this case, Z1, Z2, and they give you a surface. And you can use this to kind of, in my case, typically you have a surface where you don't know all the points and you want to know what the whole surface looks like. And you just move around your latent space and find the surface that matches closest on the places you know, and then boom, you've got a full surface. And you can then also just explore the latent space. So by nudging these variables, you get kind of a nice way to move around the space of the objects you care about. So in this case, it's a surface, but it could be some algebraic thing. And then you're just taking a walk through the possible things. And this is kind of how you explore what the autoencoder has done in order to compress your thing in a way that's understandable. And then maybe just I have a very visual one here, but so you train your thing and you say, hey, what's happening under the hood? So I'm going to show you what happened with these surfaces. So I had a three-dimensional VAE. So the latent space is three-dimensional, so you can visualize it. And you can actually see what it chose to do. So on the left-hand side, I have the reconstructed thing. And on the right-hand side, I'm moving around one of the three axes of my three-dimensional latent space. So I just chose three because we can visualize three dimensions. And as this dot moves around, basically each dot is just three numbers. And those, for each one of these three numbers, boom, I get a full surface. And you see here that somehow wiggling in this way corresponded to kind of wiggling the surface in that way. I mean, there's lots of this story, but basically these surfaces are not arbitrary. They have kind of interesting geometric constraints on them. And somehow it's capturing a little bit of that version of it. And then if you move in the other direction, we see, oh, it's capturing a different aspect of the surfaces. And this, it chose to just capture the flaring up near the front end. Any guesses as to what the third axis might do? It turns out the third axis, complete fluke, but correspond to how high or low the surface was. And it's interesting because, when I first show this plot to some people, they're like, hey, why is the dot going the opposite direction of the surface? And I say, well, because I had nothing to do with making the third dot do this. This is just how the autoencoder chose to best minimize the error. And then you could just go for a walk. And here's a knot in latent space, and you can just see what all the different reconstructions are. And I have a surface as an example here, but you could do this with a combinatorial structure. Then you can go for a walk in latent space and kind of see what the autoencoder has figured out about the structure of those objects, and whether you can kind of learn anything useful from that. So I think I'm at my speculation time number 2, which is this is actually the last slide, and then we can just discuss. But basically, the speculation time is using these kinds of things. Now you don't even have to have a specific question in mind. You fix your activation functions to be in some category you care about, say polynomials instead of non-polynomial things. You fix a class of affine transformation that you care about. Maybe you care about equivariant maps with respect to some group action. And then, can we discover optimal presentations? Can we discover the dimension of the quotient? Can we generate counterexamples? Can we generate examples? Because once again, this idea that once you've trained this beast, you can forget about the encoding half and just move around the compressed dimensions and see what it's reconstructing. And perhaps you discover that if you move in a certain direction, so here, let's go back to my example. I discover that, hey, when I go up and down, it raises and lowers the surface. So I can say, I wonder what happens when the surfaces are super, super high. And then I can just move all the way down in latent space and just look at the surfaces my autoencoder has produced. And that gives me some interesting insights, in this case, into market behavior. But in your case, perhaps it tells you about a presentation with a minimal number of non-zero things, maybe you can factor polynomials. I mean, you could also play with toy examples, right? So you could take a problem that you know how to solve exactly, and then try to see if you could train a neural net to solve that problem that you know exactly, and then use that as inspiration for an architecture for something you don't know about. I think that's
Yes.
yeah. So that's everything I had. So now I can just discuss as much as you want.
Cool. Oh, bananas. Why is it not working? So let's thank the speaker. It's my sound.
Total disaster.
Listen.
No,
volume
we didn't hear it.
It didn't. Okay. Everyone be
I think
quiet.
I did something. I had my mic on.
It's okay. One sec. Let's try this. Here, I'm gonna mute everyone. There should be an option to mute everyone. We'll try this again. Okay. Now, if there's any questions, you can unmute yourself and ask. Actually, that's a good thing for me to do in the future. Just automatically mute everyone and then go for
Do it.
Yeah.
Yeah. Go for it. Image source. What is a NWCG?
I think it's the fire nomogram earlier. It's something about
Oh, I
forest
see.
fires.
Oh, yeah.
So, oh, Vedarth has
Oh,
a
is there?
question. He's raising his hand. So
I was just gonna ask. So you said I think quantity matters more, right, for the data. So, and for example, in the problem I was working on, like this object grows very largely, very quick. So how would you try to work with like a neural net or something if you
What's
have
the object?
Oh, I was just trying to find a generalized basis, a Grosvenor basis. But it got like big very quickly, right? And the way I was trying to find it required me to, it's kind of like a recursive in a way. So I have to like kind of carry over everything from.
So you have a slow recursive algorithm to give you the answer in some cases, right?
Yeah, I didn't make one, but it's kind of the construction is kind of like that. So I was just asking, if you don't have much data, is there any way that your model can still work with like small data, or do you have to always?
Well, it depends what small and large means to you.
All right, of course, right. Okay, I see.
Basically, the bigger the net is, the more data you need, right? So if you're going to go something with millions and millions of free parameters, you're going to need a good chunk of data. You won't need as much as you think, right? So, people do have neural nets that have way more free parameters than the amount of training data that do really well. And this is kind of partly, so these low to high frequency results are trying to explain that. Like, why is it that we don't get this insane overfitting going on? Where, if you're trying to fit this crazy wild thing, and you don't have that much data, why is it not just nailing them all? And there's kind of, the buzzword is regularization. So you want to, if you don't have a lot of data, you want to turn the dials to make sure that you're forcing your net not to really, really overfit it or get more data. I mean,
Okay, thank you.
I would say start small, right? You say you don't have much data, build a tiny net.
Okay.
Train it on that small data, see what happens.
Okay, give it a try. Thank you.
So often what we're thinking about are kind of infinite sets of objects, but we look at finite slices. And so I'm wondering how to think of those in the neural net world, because like we can't necessarily for one that we really want to study, which is say gigantic, it ends up being an infinite dimensional space that we're trying to represent.
I mean, so infinite dimensional spaces are not really a problem per se. So in the PD examples I'm showing you, everything in sight is infinite dimensional. You just need to be able to sample in some pieces, right? So you want to have the dimensionality. Maybe you have a variable, which is the dimension, that keeps track of where you are in that space in your infinite filtration. and you try to, so somehow nets are pretty good at interpolating even infinite dimensional spaces, and you only give them some finite grids of points, as long as you give them one way to kind of keep track of where they are. So maybe you have this filtration, you now have examples, you might have, I mean, in the simplest case, you might have one input be where are you chopping it off? And just have it keep track of that.
I think the problem we have here is that usually, say that you have a function you don't know, but it's really, we know the first few value. So we need near zero, but we don't know what happened as you
I see,
wonder.
so it's like a counting function.
Yes. So those kind of things are a little bit.
I mean, that's hard because then you want to go into the asymptote.
Exactly.
I don't know. I mean, I guess it's not obvious how to encode asymptotics. So typically you'd want to, typically what you would do in practice actually is, you have your training domain and then you want to, what I would call fail gracefully out of domain. And that you can kind of, I mean, if you think about the ReLU activation, if you're going far out of domain, you see that you get a linear asymptote in all directions eventually.
Mm-hmm.
But you could get some interesting stuff before infinity. But I don't think that maybe figuring out, like, I think these Grosvenor basis type problems sound more amenable to this than, say, extrapolating the value of a counting function far beyond the realm where you know the answer.
No, but the problem is that we usually, like what Bedard asked you was, like he knows the value for n up to n equal 5 or 6. And going further than that require a crazy amount of computation. But still,
I mean, have you implemented it in GPUs?
Of course not.
So one thing I will say, cloud instances are cheaper than you think.
Yes. But it's not just an investment of money, it's an investment of knowledge and time.
Mm-hmm.
Yeah, there's an infrastructure to be built up more than that is more than just memory.
Mm-hmm.
Yeah, I don't think so. I was looking at like Sage and GPU. I don't think Sage inherently works with GPU, but apparently there's ways to get it to look into GPU if you want.
Because I'll say, whatever you're doing, if it involves multiplying matrices, you haven't seen anything until you've run it on GPU.
I see Kelvin nodding. He wants to do that.
Wait, do you want to do it or have you tried it, Kelvin?
I want to do it. I don't know how to do it. I have matrices that are kind of huge.
Yeah, if you're multiplying matrices, and your bottleneck is the speed, then you might be blown away by how much more you could get.
I guess personally, my problem is a bit of a memory issue. Like I want to do, like this might be very specific. Sometimes I want to do Gaussian elimination on an enormous matrix, and my computer, like I don't have a huge computer, and it just crashes after.
You could try to be smart and in your implementation and not use as much memory. I think a lot of us are guilty of that when we're writing programs, is that we don't really pay attention to our garbage collection. And so you can probably, if you're doing Gaussian elimination, you don't need to keep track of the whole matrix the whole time, right? You're not keeping several copies of the huge matrix.
Yeah, certainly. There are certainly places that we can, like, sometimes I want to be quick and hit end like 3 lines of code and let Sage do it, but.
I mean, I don't know if Sage is implemented to be fast. I think, isn't it implemented more to be usable?
Both-ish.
It's supposed to be both-ish. It's
Yeah.
supposed to be, for small example, not caring, and for big example, starting to be more wise about how data is manipulated.
Yeah.
That was the idea initially in Sage, but I don't know where they are. It's a monster.
I think when they can, when someone sees like a more efficient way of doing something, they'll definitely implement a faster algorithm. But it's never, I don't think it's ever like the first step of any algorithm is inherently the fastest one that's out there. So it's fast-ish. So you can,
And
if
sure.
you do find a faster algorithm for something, they're always welcome to be like, hey, let's implement this in. But people
But
have to actually
I would
want
bet
to do
they don't do GPU because most people don't have some at home, right?
Well, so
So
that's what I was saying. So currently there's no GPU integration, and from what I could see on Ask SageMath, it's because just no one's integrated the two. No one's had the time to put that into SageMath. There are ways to do it apparently, but it's just since it's all voluntarily run, someone has to actually be like, "Yo, I want to do this," and since no one's done that, it's kind of just sat there.
We need to organize a Sage days around
to get GPU running.
Yes, no, that is exactly how those things get
Yeah, that's okay. I'll figure it out.
There you go.
That's this is actually how it's done. You say you're doing it.
No, the way
Kelvin, you're helping me since you want GPUs for matrices too. Bam. We'll make it happen.
Yeah, you make
mean,
it
if you
happen
want.
by organizing a Sage days, writing the grant proposals, and then inviting the people who can do it, and saying, "Hey, I'm gonna commit you for 3 days time to finish this project." And
Oh yeah, we can figure something out.
It does work because then they go home and finish it, but they get it started.
Yeah. Well, I'm wondering if because the GPU processing thing is actually is a big infrastructural change that would probably need to happen. I think I don't know too much, but I have to look at it.
If you have matrices and you're multiplying them, sometimes it's that simple as just moving to what they call tensors.
Well, I mean, so it's like if we're just doing GPU for matrices, that's one thing. But like, I think generally when we're talking about adding GPU infrastructure to Sage, we're talking adding it to like Sage.
The whole thing, yeah.
Yeah, and that's going to be a little more intense. But doing it just for matrices as a like starting point might be would definitely be kind of where we probably land.
Yeah, well, I mean, I think you would start with certain features that you want to say, and you build those separately, and then you do an interface to that.
Yeah.
And so in the case of matrix multiplication, you would say, okay, I'm going to build that separately, and then have Sage call that in order to actually complete its function.
Yeah, we can figure something out.
Just a quick comment on the computer limitation. So I've had some problems before, especially with TensorFlow. And what I've done was I started using Google Colab, which was developed by Google, and we don't run on our machine. I use their server to run my models. So like it runs really well, but I don't know if it solves the problem here.
Well, that's kind of what I was getting at with cloud instances. Like you could don't run on your local machine. Basically, it's cheaper than you think to go out there and.
Yeah, definitely.
Time to ask Natal for funding.
He just said cheaper.
I don't think it's cheaper than zero Nantel.
Okay.
Like, I guess I say cheaper, like it's not like thousands of dollars.
But, so
probably pennies if you're not doing too much.
Well, it should be free if it's pennies.
Well, the Google Colab,
They don't want to collect. They don't want to collect your pennies.
I mean, it depends how many pennies, right? 1 million pennies is quite a lot.
Yes. Okay.
Are there any other questions?
I'm done. Thank you so much.
Seeing none. Where did my mouse go? Okay, seeing none. Let's thank the speaker again.